Thank you, Jan. So I would like to thank the organizers for inviting me here. It's a great honor, especially on such an occasion. And like many of us, I was greatly influenced by Maxim. So I'll talk today about connection between math and physics. So I'm a physicist, and I'm interested in physics component of the story, but it's a nice bridge between what I'll explain to you as very rich mathematics and very rich physics. So every talk is a delicate balance between telling the truth, meaning presenting all the details, proving all the theorems, explaining everything. But then there is a danger that we'll be bogged down on those details and we'll never see the big picture. So I'll try to make this delicate balance between presenting big picture with lots of pictures and also some of the concrete results and examples. So I'll try to emphasize those points where I'll have at least two concrete results in this talk. One is going to be concrete new results for mathematics using this correspondence that I'll explain, and one will be actually new result for physics. Mathematicians in the audience probably don't care if there is a new result for physics, but I certainly do. And of course, all the details that I'm going to miss in trying to maintain this delicate balance could be found in some of the papers I mentioned here with two great guys, Abhijit Gade and Pavel Putrov. So what we'll really do in this talk is we'll study, well, as this physics guy says, Fivebranes on co-associative four manifolds inside a G2 holonomy space. And that's actually what we're going to do throughout this talk in this hour. And there is a famous cartoon which shows there are different versions of it. This is for IT guys. This is you tell dogs something and they hear okay, ginger, blah, 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 ginger, and so on. So similar in this opening line, there are some words which may be very familiar to you, but there might be some words which are terribly mysterious. For example, I'm imagining to mathematicians, the word fivebrane is very mysterious, and everything else probably is more or less familiar, maybe not too well, but at least it's from math. For physicists, actually the situation is reversed, I have to say. Physicists really understand only one word, fivebrane, and all this co-associative four-manifold G2 holonomy space. To physicists, actually, that's even worse. So anyway, I'll try to explain what the fivebrane is. So since I'm aiming this talk more for a mathematical audience, what are fivebranes? These are very rich, interesting objects in 11-dimensional M theory, and they have a lot of rich structure, but at the zero level of approximation, they're just 6-dimensional submanifolds. So these are certain gadgets supported on 6 manifolds inside 11-dimensional spacetime. That's all you have to know. They do carry some additional structure. For example, beyond the zero level of approximation, you can have multiple such subvarieties, and then multiplicity gives rise to symmetry, which is typically UN or SUN. That's what we're going to consider in this talk most of the time. So there'll be G, which is either UN or SUN, some group, compact group of Cartan type A, and N here will refer to multiplicity of those 6-dimensional subspaces in 11-dimensional spacetime. So here, this picture is illustrating, this is cartoon for such embedded hypersurface in big space. And now the idea, which goes back all the way to Kalutzay-Klein, but have actually far-reaching consequences, especially for us, is that what we'll do, the kind of game we'll play, is that we'll try to take this 6-dimensional object, 6-dimensional fivebrane, and split its 6 dimensions into compact manifold Mn, which is what we'll aim to study, and the remaining part will be just a flat Euclidean space of dimension 6 minus n. So here I'm using kind of obvious, if you wish, I'll refer to this kind of decomposition later on as 6 equals n plus whatever is left, 6 minus n. The consequence of this, and again, physicists can tell you more and more about it, but this will be not just an extra talk, it will be a whole big course, how some theory, this extra data which lives in 6 dimensions, upon wrapping the 6-dimensional big space-time on some manifold of dimension n gives rise to some effective field theory in 6 minus n dimensions, which is labeled by space on which you compactify, by this compact manifold Mn. So this idea is fairly simple, and again, it's 100 years old, but its implementation for us will be fairly interesting and quite rich. So just the very fact that Fivebranes exist makes all these theories, lower dimensional theories in Euclidean dimension 6 minus n, labeled by other manifolds exist. So that's already basic fact, which is kind of punchline of the talk, if you wish. I'll, of course, put lots of bells and whistles on it. We'll explore it. But that's the idea. And it's fairly simple. So, by the way, if you have any questions at any point, feel free to interrupt me.
So conformal field series 6 dimensions, which also, they're labeled by ADE, yeah?
Yes. So that's essentially the same story. So that's a 6-dimensional conformal field theory which lives on this Fivebrane. So these terms are completely interchangeable. And for me, ADE will be always of Cartan type A. So that's the same story, indeed. Yeah, so the good point about this lower dimensional theory, which will be obviously in dimensions less than 6, is that such a theory, upon compactifying the 6D theory on manifold Mn, will actually depend on topology and also on geometry of the manifold M of dimension n that you choose. So this is, if you wish, a functor which sets n-dimensional manifolds into 6 minus n-dimensional theories, physical theories. That's a kind of funny functor, very strange object. But we're going to explore its consequences. And I'll start with something that's by now fairly well understood, at least many aspects of the story are well understood, and we'll play the game where we're going to split these 6 dimensions in different ways. So first, here I'll split 6 as 3 plus 3. And then, of course, we'll come to 4 manifolds and split it into 4 plus 2. So again, this is kind of simple algebra to keep in mind. So if you choose a 3 manifold, this little n equals 3, then complementary dimension is also 3. So what you get is a 3-dimensional theory, I'll call it T of M3, which is labeled by a 3-manifold that you want. It carries certain supersymmetry. Again, there are lots of bells and whistles, but in the first round of approximation, I'm going to skip that. Now, you can view this construction, and that's the modern perspective on things, as constructing invariants of 3 manifolds and 4 manifolds, which are of completely different type that are not very familiar, that we don't usually think of. When we think of invariants of 3 manifolds, 4 manifolds, we typically think of numerical invariants. In recent years, people start talking about invariants of, say, knots and 3 manifolds, which take values in vector spaces. These are a categorification of numerical invariants. But this is something even more esoteric or weird in the sense that to a 3-manifold or 4-manifold, we associate a physical theory. And theory in dimension 6 minus n would actually be of high categorical nature. It will be something that is not just a number, is not a vector space, but contains a lot of information, whole load of information, a lot more than just a number.
M3, is it compact or how's the boundary on this?
Boundary of which? Oh, 3 manifolds, for instance. You can develop the story where you have 3 manifolds with boundary, without boundary, so it's a good question. In other words, in this context, it's a perfectly valid question, and boundary, of course, will be important if it's present. If it's not, then it's not. Good thing is that you can recover some of the more familiar invariants of 3 manifolds, 4 manifolds, by trying to take this physical theory and ask a question, okay, what is the partition function of that theory? That, of course, is going to be number of function. You can ask about correlation function, something that Nikita considered in his talk, or various other gauges. For instance, simple question is to ask about supersymmetric vacua. I try to omit all the words infrared because I thought mathematicians don't know them, but now they do. So therefore, this is really about infrared physics of such theory. You can ask, say, what are supersymmetric vacua? Many of such theories, even in 3 dimensions, can be described by Landau-Ginzburg type potential function W. That's a holomorphic function exactly of the same type. And these are close cousins of 2-dimensional theories that we heard in previous talk. And this will be certain space. It may consist of isolated points. It may consist of continuous subvariety moduli space. But in any case, what happens is that this space of supersymmetric vacuum is nothing but space of flat connections on a three-manifold M3. So if you start with AD fivebranes of this AD type, which for us will be either SUN or UN of type A, then this will be complex flat connections for the same complexified Lie algebra. So at least this theory, it's not some stupid functor which takes three manifolds into some mysterious theory. It actually knows about, say, flat connections or character variety on a three manifold. So that's one statement. And once you start exploring this correspondence, basically the game of the rule of the game is that you explore different invariants of this theory in lower dimensions, in 6 minus d dimensions, and ask for, again, different gadgets and field theory language, and try to recover different invariants of 3-manifold, 4-manifold, and so on. Here I give an example. Say M3 is a length space. Say S3 mod zk, and fundamental group is zk. Basically, complex flat connections, just like real flat connections, are parameterized by homomorphisms from fundamental group, in this case zk, into the group G, modular conjugation. So this is a finite set. Okay? A nice interesting fact is that this finite set happens to be labeled by same type of label, which labels highest weight integrable representations of the loop group at level k. So this may be viewed at this level as a coincidence, but in fact, you can try to work out what this theory, three-dimensional theory, should be for length space, and then you're going to find. So I'll erase this and save it for later. So theory associated to length space, say K1, is Chern-Simons theory. In fact, certain supersymmetric extension of Chern-Simons theory, but that won't be important to us at level K. Because if you ask yourself, have I seen this somewhere, this indeed is the space of ground states in Chern-Simons theory, either supersymmetric or not. So if you think of vacua being flat connections, then already this basic fact suggests that the theory associated to length space should be some version of Chern-Simons. And it will play a role for us later. Now, you can ask about three manifolds which do have boundaries. So for instance, if you ask about knot complements, which is another nice class of three manifolds with a toral boundary, either knot complements or link complements, then in this case, complex flat connections will come in families. In particular, if you talk about knot or link with a single component, there is this famous A polynomial whose zero locus defines for you the character variety. And this is exactly the space of critical points for three-dimensional theory, which is associated to knot or link complement. And again, this is a nice class of examples. By studying this correspondence in present context, you can derive various versions of so-called volume conjecture. One of the versions says that there is an operator which in physical theory on this side of the correspondence is some sort of word identity, very much like in Nikita's talk, that annihilates partition function. So, and then there are various upgrades which even get to homological invariants that I'll mention very briefly in a second. So this partition function z of m, what is this partition function? Well, you could think that if you already have access to space of classical solutions in Chern-Simons theory, namely flat connections, there should be a way to quantize it, namely to construct the full Chern-Simons partition function of a three-manifold M3. So now Chern-Simons appears on this side, whereas a moment ago I was talking about Chern-Simons on this side of 3 plus 3 split. Now, yeah, there is such a gadget, and there is a question about three-dimensional field theory T of M3, such that answer to that question is actually Chern-Simons partition function on a manifold M3. The corresponding question here involves turning on omega background, very much like in Nikita's talk, and counting instantons, except that the problem here is lower dimensional. So Nikita studied this omega deformation of four-dimensional gauge theory, where you have 4 dimensions of space-time. Both of them are considered in equivariant context. This is a baby version where instead of instantons, one has a sum of vortices, very much like in the work of Taubes and so on. And again, one considers equivariant vortices, meaning they live on a plane, and we're trying to look at their representation with respect to rotation group in 2 out of 3 dimensions on this side. And that's a very well-defined quantity. Physicists study it, and funny enough, they recover complex Chern-Simons partition function over 3-manifold M3. So that's the relation here.
Sorry, the partition function is what? Is the vector in a Hilbert space, or this quantization of the boundary? What's the left-hand side as a number?
Generator?
Correct. So it's indeed a vector now in the case of 3-manifold with boundary, this will be a vector in the Hilbert space of associated to the boundary. Yeah, exactly. So in particular, in this context, it depends on parameters, well, these are some of these parameters, and on one side of the correspondence here, this operator equation, this word identity, is known as quantum volume conjecture, or some sort of AJ volume conjecture. And on this side of the correspondence, this is a statement that quantization or a certain operator relation associated with classical moduli space, because the zero locus of A was the classical moduli space of vacuum for a 3-dimensional theory here, annihilates this vortex partition function. So this statement has a meaning both in this world and this world, and luckily they agree. So again, there are lots of papers on the so-called 3D correspondence. By now, this is fairly big industry, and I'll just mention a couple of such applications. But my goal will be eventually to actually move to the next level and try to develop the same sort of dictionary or industry for studying theories labeled by 4 manifolds, because this is much more mysterious, both in physics and math. And to my mind, this is much, much cooler. Finally, I kind of suppressed, for sake of presentation, the fact that there is some supersymmetry in this 3-dimensional theory which is labeled by 3-manifold. And this didn't play much role even in the example I mentioned here, but it is supersymmetric, and as such it has supercharge, so therefore you can ask for invariant or object associated to this theory, which is neither space of vacuum nor some number, such as partition function of a certain kind, but rather a space. Namely, a space of states which are annihilated by supercharged Q, but not Q exact. So in other words, we can ask, what is the Q cohomology in this theory which is labeled by 3-manifold? If theory itself is defined by 3-manifold and we ask for a certain question about it, the answer should also be something that knows about 3-manifold. And again, if we talk about not complements, what's interesting is that this Q cohomology recovers mathematically defined Khovanov homology and its variants. So that's an interesting.
So on the left-hand side, H stands for Khovanov double-graded.
Yeah, so here on the left-hand side, H actually stands for SLN version of Khovanov homology, in fact, decorated perhaps with various representations. Basically, categorification of quantum group invariants, doubly graded space. And in physics literature, such elements of Q cohomology are sometimes referred as BPS states. BPS states are so-called supersymmetric states. These are states in the theory which are annihilated by Q but not Q exact. So that's a definition. So sometimes the statement is mentioned as not homology being interpreted as a space of either supersymmetric or BPS states. Now, until so far, I talked about the 6-dimensional theory, and we didn't even consider where it lives. It actually lives in big 11-dimensional ambient space, and that embedding of 6-dimensional subvariety in big 11-dimensional space is not arbitrary. Basically, the picture is as follows. The 11-dimensional space consists of R5, 5-dimensional vector space, and Calabi-Yau, which for most of the discussion we can take to be just total space of the cotangent bundle to 3-manifold here. After all, neighborhood of any Lagrangian inside calabi-Yau looks like that, so that will be good enough. And we'll split some of the dimensions of the vector spaces which are not used or not curved in the following fashion. R will be singled out and usually is interpreted as time. Think of time as in Floer theory, and it will be useful in a second. And the rest is subject to this equivariant omega deformation, which gives rise to Q grading and homological grading in application to not homologies. So again, total world volume or support of this Fivebranes is equal to 6. So this is our 3 plus 3 split. This manifold is interesting, curved, has interesting topology and geometry that we want to detect. Here, in this R3, lives the three-dimensional theory I was discussing on the previous slide. And it's embedded like this in ambient 11-dimensional space. I want to point out already here that there is a 4-manifold inside, which will be much more interesting in the rest of the talk. Namely, if you combine the time, which didn't participate in rotation symmetries that we used, and 3-manifold here, this is basically indeed like a Floer homology picture where you have some non-trivial slice and across time, Floer time, and together they make a 4-manifold R cross M3. So that's the first remark in passing. We'll come back to it in a second. Second remark I want to make about this embedding is that you can look at this picture from many different viewpoints. That's very typical in physics. You can study the system from one perspective, from another perspective. You can look at it, for instance, from this point of view of R3 here, which gives some three-dimensional theory labeled by 3-manifold. Or you can look at this picture from the viewpoint of ambient spacetime, in particular from the viewpoint of the calabi-Yau here. And then it gives rise to a certain enumerative problem. What we call by this a space of BPS states in that context is more appropriately known as a space of so-called open and refined BPS states. So there are many ways to approach this problem. Now, what I'm going to do later is something to which I alluded before, is consider this R cross M3 and not just let it be a direct product, but rather consider evolution of a 3-manifold along R. In other words, consider non-trivial cobordisms. For instance, here is a cartoon which represents cobordism between, say, two link complements, and this will give rise to a functor between different link homologies. Now, such functors are all very interesting, and again, if you ask yourself a question in this embedding of not homology in a physical setup, how would cobordisms play a role? This is how they would appear. They would take one of the dimensions of this 11-dimensional picture, which has not been used, and combine it with M3 into a 4-manifold. So if you want to study functors acting on homological knot invariance, which is something that I've been studying in the past several years, you are inevitably coming to the picture of 4-manifolds, which are cobordisms. Another interesting fact I want to mention here is that among all such cobordisms, there is something special. In particular, among all knots, unknot plays a very special role for the following reason. So suppose you have a knot such as, say, this trefoil here. And suppose you take a copy of unknot, very much as shown over there, and we want to consider cobordism from here to their connected sum. So unknot is special in the following way, that if you take a connected sum of unknot with any other knot, then it doesn't change the knot. So gluing this or reconnecting it in a way like shown here basically gives me back the trefoil knot, which was what we started with. So as a result, we get the following statement that cohomology of the unknot, even from the knot theory perspective, is an algebra that acts on cohomology of every other knot, say in this case trefoil. And this is a fairly general argument, which again might be very tricky in several versions of various versions of knot homologies, but this is the basic idea, that's the origin. And another interesting observation is that it happens that in the realization here, the cohomology of the unknot, which is this algebra, is also algebra of so-called closed BPS states. In this context, they just coincide, whereas their origin is rather different. This comes from knot theory and can be computed by known techniques in low-dimensional topology. This has enumerative origin and was studied by Nagao and Nakajima. In fact, both of these depend on choice of chamber and so on, but they just coincide at the level of answers. And in fact, what this will suggest then is that so-called closed BPS algebra acts on the space of open BPS states. This is a more general statement, and in the context of closed BPS states, this goes back to work of Harvey and Moore, who conjectured that closed BPS states form an algebra. In the language of my previous speaker, where if you have something finite, something infinite, you combine them, you get something infinite. Here I could say that if you have closed and closed, you combine them, you still get something which is closed. However, this is no longer true if you have closed and open. When you combine them in a mysterious product operation that physicists call forming bound state, you get something which is still open. So closed times open is actually open. And for this basic reason, we conjectured with Markus Tosic that open BPS states form a module or representation of the algebra of closed BPS states. And of course,
About algebras, we can really relate things with Harvey and Moore because in what we've done with Jan, we use kind of P structure, and is it natural from physics?
Right. So this is
trouble for many years to make it really kind of
right. So there are completely different versions of algebra structure on the space of BPS states, and in fact, from you and Jan, I've been learning a lot about even different connections, including, say, motivic, homological, whole algebra. So I don't know which one of them will be proper mathematical home for this picture, but at least, again, at the physical level, that's the story. I would just say that that's the same algebra as Harvey and Moore used. And I agree, that's a good question. For me, again, this was kind of digression about BPS states. What I was trying to illustrate really is that given a theory, there are many questions you can ask to pass from big full-fledged theory, which probably should be described by categories, high categorical structure, to numerical invariants and vector spaces, just like this Q cohomology. So there are many questions you can ask to get from very complicated esoteric field theory down to numerical invariant, if you wish. So now I'll try to come back to this previous setup and really push a little bit further these cobordisms between, say, different three manifolds, which, as I mentioned earlier, naturally lead us to the world of four manifolds. So I'm going to take this R cross M3 and replace it by a general four manifold M4, could be cobordism. Then, in order to preserve supersymmetry, and for other reasons, what's going to happen is that on this upper part of the slide, the space-time R, which was unused, will naturally combine with Calabi-Yau geometry into something seven-dimensional. And this something seven-dimensional here is a very boring version of G2 manifold, but more generally, if this is non-trivial four manifold, then it will sit as co-associative, so-called co-associative cycle inside much more interesting G2 manifold, which will be locally the total space of self-dual two forms on M4. So, and this is the cartoon, which represents this co-associative four manifold interpolating between M3 and M3 prime. And the ambient space is a G2 holonomy space of dimension 7, which has two boundaries, Calabi-Yau prime, associated to the three manifolds here. Now, in a physical picture, again, I'll start coming back to using this Fivebrane theory and asking, okay, if three manifold before gave me a three-dimensional theory, then what about this four-dimensional cobordism? And then later on, more general four manifolds. What do they correspond to? Well, because total dimension has to be 6, the four-dimensional cobordism will give rise to something two-dimensional, because 2 plus 4 is 6. And it has to interpolate, or in this case, be the interface of three-dimensional theories which are labeled by the corresponding boundary components. That's a general principle that you can just get from dimension counting. So again, this was a long introduction or motivation, if you wish, to very basic principle, which I could have started after the second slide, said instead of going through this three-dimensional 3 plus 3 correspondence, I could have said, OK, let's just do 2 plus 4. So I'm going to play the same game here, but this detour or digression in three-dimensional 3 plus 3 correspondence is actually going to be very useful because we'll consider 4 manifolds with boundaries, and we'll be gluing 4 manifolds as well. OK, so given a 4 manifold, you get some kind of two-dimensional theory, which is labeled by 4 manifold, and by the same general principle, it will depend on geometry and topology of M4. And this is where the story starts, and that's where the interesting dictionary unfolds. The reason is that 4 manifolds are much more interesting than 3 manifolds. And for many years, I've been studying not homologies in the context of physics, BPS states, and so on. But mathematicians always ask me, why are you doing this? We are studying knots because this is beginning of 4 manifolds for us. And I constantly resisted because knots were much easier, and 4 manifolds are much, much more complicated. So this is what I mean by saying that it's very rich math. And if you think about it, then the class of two-dimensional theories that you get by compactifying 6D theory on, or 6-dimensional Fivebranes on 4 manifolds, it also has very rich physics. Supersymmetry here is very low, so there is very little control. And a lot of kinds of things that can happen in physics happen in this context. So even things like dynamical supersymmetry breaking, which is something that actually occurs in the real world, possibly. Yeah?
So if you take this 2D theory and say you do some kind of half twist or something, how much of the geometry of the 4 manifold does it depend on?
I'll answer exactly this question in 2 slides. Excellent question. So now we'll play the same game. We have a complicated functor which takes 4 manifold and associates to a 2-dimensional field theory. Luckily, this 2-dimensional field theory is not something general. It's actually it's going to flow to conformal theory in the infrared. Now mathematicians know what these words mean. So in particular, in 2 dimensions, field theories are not that mysterious. Conformal theories, for instance, are vertex operator algebras. So there is probably a mathematical framework for what I'm going to tell you. Because as dimension of this Mn increases, dimension of this theory dimensionality decreases, so we get to more and more conventional things. Now we're in dimension 2. Now, there are several things you can ask about 2-dimensional theory. One thing you can ask is its elliptic genus, which actually already appeared in one of the previous talks. In fact, Yuri Chinkel mentioned that. And this amount of supersymmetry is just barely enough to allow for existence of elliptic genus. So you can ask, what is such elliptic genus? Or I'll ask a refined question, what is equivariant elliptic genus? Because this theory turns out to have certain global symmetries, similar to what Nikita had in his talk. So one can refine this notion of elliptic genus to keep track of those symmetries as well. So it turns out, well, elliptic genus, very roughly, if you've never seen it before, is kind of Euler characteristic, or refined version of Euler characteristic. It turns out that if you use this dictionary and ask, what does it capture about 4 manifold, it captures Euler characteristics of moduli spaces of instantons on a 4 manifold. So here n is the second Chern class. This c is the first Chern class of the gauge bundle. You solve self-duality equations in each case for fixed values of second Chern class and first Chern class. You get some moduli space. You take its Euler characteristic. You arrange everything in the generating function, and claim is that that's exactly the elliptic genus of this theory, which is labeled by 4 manifold.
You sum over C as well?
Yes, you do, and that's this equivariant extension, right, on the other side of the correspondence. Now, non-trivial fact or check, if you wish, is that elliptic genus is famous because it has some modular properties for certain obvious reasons, which I'll show on the next slide, and much less obvious is the fact that this generating function of Euler characteristics also supposed to have some modular properties. So this 2-dimensional theory could be very boring invariant of a 4 manifold. But this already shows that it's not, that it knows something about early characteristics of moduli spaces. And here, modularity has to do with work of Waffe and Witten, who studied this function. And their path was, in fact, not so different from what I'm considering here. They considered the 6-dimensional Fivebranes on 2-dimensional torus cross our 4-manifold of interest. Then if you assume that M4 is kind of curved small manifold and try to forget about it, what you get is a 2-dimensional theory on a torus, which is labeled by M4. If you go the other way, what you get, and compactify on a 2 torus first, you actually get 4-dimensional superanneals, because you go from 6 dimensions to 4 dimensions, reducing on a 2 torus. And this symmetry of SL2Z symmetry of T2 becomes the famous electric magnetic duality group of Young-Mills on 4-manifold. And it's some topological version of this Young-Mills because M4 is curved. And they conjecture that this object has to have certain modularity properties. So unfortunately, well, this would be fantastic. And even at the level of early characteristics, we would love to have some access to moduli spaces of instantons on general 4-manifolds. Unfortunately, it's very hard to construct these moduli spaces explicitly. Unfortunately, we have very little access to even their early characteristics. So if I ask physicists or mathematicians, in which cases do we know this generating function of early characteristics of moduli spaces of instantons on some 4-manifold, the answer in this big space of 4-manifolds will be just here and maybe a couple of other points. So this point is K3 surface. This is what's sometimes referred as del Pezzo 9 or half K3. And then probably a couple of del Pezzos above here would be the only examples for which until so far we can write down this generating function. So that's very bad because, as you see, this is big geography and botany of 4-manifolds. And part of my motivation is to explore this territory way beyond these poor points, even at the level of compact manifolds. And what I'll try to do is I'll try to present to you some new results which allow to construct this early characteristics of moduli spaces of instantons and gain some information way above this example. So kind of push it way beyond what was known. Now, you could ask, OK, what about instantons on non-compact 4-manifolds? Well, there is a famous construction, ADHM construction at Yi, Drinfeld, Hitchin, and Manin of instantons on R4. And Nakajima provided what could be viewed as generalization of that construction by looking at instantons on LE space. By the way, LE spaces, which will play some role for me later, are bounded by 3-manifold, which is precisely the length space of the type that I mentioned as one of my examples. And that's, of course, not an accident. I'm trying to be efficient and use every information that appeared on the slides. Now, Nakajima looked at this generating series, again, of early characteristics of moduli spaces of instantons, summed them up together. So we have considered bundles of different topology and sum up the results all together. And what he found is that the result is actually a character of affine Kac-Moody algebra, where the algebra itself is determined by topology, in this case by the Dinking diagram of Cartan type A, whereas the level of the representation here, whose character we obtain, is determined by rank of the group. If you study UN or SUN instantons, then this will be the level of representation. So the role of the geometry of the 4-manifold determines the Kac-Moody algebra, and the rank of the group on the instanton side determines the level of this representation. Okay, so that's essentially the only result, which again was available until recently, about such early characteristics in non-compact context. So you can view what I'm going to tell you next as attempt to generalize this. My goal will be to use this big technology to generalize even this statement. For us, in this correspondence, this character is interpreted as elliptic genus of some theory which is associated to a K-manifold and a D-type UN or SUN. Now, I'll show you the first new result, which was derived using this correspondence between four manifolds and two-dimensional theories. But in retrospect, there is nothing that prevented us from saying, or somebody saying this back 20 years ago. And this is really very simple. So the idea is the following. Suppose you have AK minus 1 manifold. This is a four manifold whose second homology group has intersection form of type AK minus 1. And suppose you want to build AK manifold by attaching to it another piece, which contains 1-2 cycle. And again, I'll use proper mathematical language in a second. So that altogether, you have AK manifold. Now, we already know if this is a TQFT, then we know that partition function of the big thing, AK, should be, roughly speaking, sum over boundary conditions. I'll denote them by rho on the gluing along this 3 manifold of partition function for AK minus 1 and partition function for this cobordism, I'll call it B. Okay? So this is, again, a basic fact about essentially any TQFT, and Waffe-Witten tell us that this partition function comes from a TQFT. So if it really behaves as TQFT or even some relaxed version of this, you would expect that this formula should be true. Now, let's combine this with what Nakajima told us 20 years ago. He said that this is a character chi of AK minus 1. This, he said, is a character of AK. And what I'm trying to do is I'm trying to determine what is the Z of B, the partition function associated to cobordism. So the statement that is my first new result here is that this partition function Z of B, which is the sum of Euler characteristics of moduli spaces of instantons, now on bordism B, is something that's called a branching function of a coset model. So branching function of a coset theory. It's a certain object which arises precisely as decomposition of characters of one group or algebra G into characters of a smaller algebra. And here is the trick, that the Lie type of algebra, affine Kac-Moody algebra in this problem, was determined by topology of the four manifold. So as we're trying to make the four manifold bigger and glue some pieces, which are this bordism or cobordisms, we're basically changing the type of this Lie algebra in Nakajima result. And if you ask a physicist, or in fact, I think many mathematicians from, again, vertex algebra perspective know this, how characters decompose, they do decompose like this. So there is a summation over, say, rho prime. This will be rho. And this guy will be labeled by rho prime and rho. And the only unknown ingredient here, that cobordism B, then is precisely the branching function. So that's a very well-known fact, and therefore consistency of such gluing immediately leads you to postulate that the generating function of moduli spaces of instantons on such cobordism is the branching function, this C rho rho prime, which is this object here. So that's, again, the first new result. And it can be now used to start gluing these cobordisms in different ways to get a lot of new things. Just go way beyond ADE-type LE spaces, which Nakajima studied, to construct results for instanton moduli space Euler characteristics on much more general four manifolds, which you can get by gluing such pieces together in completely different order. So that's one result. Again, here the slide essentially explains the same thing I just told you. So again, if you know basically partition function for big four manifold for its smaller piece, then you can extract this coefficient, which is supposed to be labeled by boundary conditions. In this case, boundaries are length spaces LK1, LK plus 1. which I call rho and rho prime, and you're summing over boundary conditions here, and then again, very, very general argument will immediately tell you that that should be a branching function. So it's a very well-defined concrete object. Now, again, I'm playing this sort of game where we start with the 4-manifold, we construct some theory which is labeled by 4-manifold and group G, which is either UN or SUN. And then the point is, any question that you're going to ask about this theory, two-dimensional theory, will be some sort of manifold, 4-manifold invariant. Here, I ask the question about elliptic genus of this two-dimensional theory. And as I try to explain to you in this few minutes, it captures interesting information about 4-manifold, namely it captures information about Euler characteristics of instanton moduli spaces, which is probably not too surprising because elliptic genus, after all, is also Euler characteristic, more or less conceptually. Well, you can ask a question about Q cohomology. This is exactly a question Kevin asked me. So if you do the half twist and ask about ground states, that's the same as asking about Q cohomology in this theory. Again, there is a supercharge. And if you think about it, what it translates to is a statement about Donaldson invariance. So Donaldson observables and their multiplication ring is precisely the chiral ring in this half-twisted theory, or put differently, it's a ring of Q closed modular Q exact operators in this theory. So this theory, which is again a very funny invariant of a 4-manifold, is not so dumb after all. It knows about moduli spaces. Well, it knows about their Euler characteristics. It knows about intersection form. Well, you can also associate a very different type of invariance to this two-dimensional theory. Here we had some numerical invariance. We had some spaces and their intersection cohomology. One can also ask about space of marginal couplings in this two-dimensional theory. That's a very well-defined physical question. It spits out some geometry as an output, and I have no idea what this geometry means for the 4-manifold. So it's some manifold parametrized by M4. Or labeled by M4. So there are lots of kinds of questions you can ask, and this allows you to build a dictionary between again, 4-manifold and various observables in this two-dimensional theory, which is labeled by 4-manifold. Okay, any questions? All right, so in the next in the remainder of the talk, I'll try to say a few words how one can build such two-dimensional theories very concretely. So if you want to implement this dictionary, it would be useful to know how to construct this two-dimensional theory. So we can take various invariants of this 2D theory, and it will be invariant of a 4-manifold. We already talked about cobordisms. In fact, I tried to explain that if you're studying functors acting on homological knot invariants, you very quickly run to problem of studying cobordisms between 3-manifolds or maybe 3-manifolds with knots. So here I want to do something opposite and consider 4-manifold, which is stretched along M3. So this is a neck whose cross-section is a certain 3-manifold. Then again, the same principle that total dimension should add up to 6 quickly tells you that, well, and we already know that to a 3-manifold you associate some 3-dimensional theory, but when it's kept off, on the left or on the right, you get a 2-dimensional manifold because total dimension is 6. So if you borrow 4 dimensions in here, you're left only with 2 dimensions in the external space. And what this describes is it describes 2 boundary conditions for this 3-dimensional theory, which is labeled by TM3. And one boundary condition is labeled by this 4-manifold with boundary. Another boundary condition is labeled by another 4-manifold with boundary, which are glued together along the neck M3 cross the interval. So the basic idea in this whole program is to chop 4-manifolds in basic pieces and then start gluing them together so you can glue the theory associated to a closed 4-manifold from basic building blocks. In the past work with various collaborators, we successfully implemented the same process for building 3-dimensional theories associated to 3-manifolds by chopping 3-manifolds in basic pieces and again gluing them together. So in the world of 4-manifolds, and now I have to be a little bit more and more concrete as we progress, the basic pieces and the basic construction is usually based on handle decomposition. This picture is borrowed, this beautiful picture is borrowed from Akbulut book. You start with a 0 handle, which is basically 4-ball, then glue on top of it 1 handle, 2 handles, 3 handles, and 4 handles. The last 2, in good cases, can be attached in a unique way. Also, to make life simple, most of the time I'll assume that there are no 1 handles. So we just deal with such handle decomposition, which involves only 2 handles and therefore only 2 cycles. So simply connected four manifolds. Information about such handles is usually encoded by drawing pictures on the boundary of this 0 handle, which is a 4-dimensional ball. Its boundary is a 3-sphere, shown here. And what one usually draws is touching circles of 1 handles and 2 handles. 1 handle is represented by embedded circle, which could be knotted, could be unknotted, and labeled by a bullet. But attaching circle of a 2 handle is shown by usual type of knot and decorated with a number, integer number, which is early number that describes the normal bundle of this attaching circle, or normal or handle, 2 handle. So in the end, if you're interested in, say, 4 manifolds which are simply connected and built out of handles, the picture is that you have a bunch of knots, very much like a knot theory, except that you decorate them with integers, which are called Euler numbers, and that encodes the information. This is how you label 4 manifolds. So next step is to construct theories, 2-dimensional theories, which are labeled by this sort of data, or start gluing them together. In this case, intersection form on second cohomology of a 4 manifold is basically given by linking numbers of these knots, if I and j are different, or simply by these Euler numbers if you're talking about self-linking. So sometimes, again, this was general picture. If your knots are all unknots, then it's much easier to encode the same information by so-called plumbing graph. So if you have, say, Kirby diagram, which consists of a bunch of unknots linked together in this chain type manner, then effectively what you can do, you can encode the same intersection form by drawing this quiver type diagram or graph called plumbing graph, where each node corresponds to a 2 handle. And again, it only works if the corresponding circle is unknotted. If it's unknot, doesn't have knottedness itself. And then all you have to do is to draw these bullets, draw lines whenever they're linked, and again decorate everything with these integers, which are Euler numbers. So this is, for instance, the Kirby diagram and the corresponding plumbing graph of the E8 manifold. Okay? I want to point out that it doesn't always work. Even if you work with just unknotted circles, then this is a good example of a 4 manifold which is bounded by 4 torus. Here, the linking number between each of the 2 circles is 0, so unfortunately you run into conflict and you cannot describe it by any kind of plumbing graph like this. So it only works for some type of 4 manifolds. Now, let's come back and revisit what we discussed before. You can build many 4 manifolds, very large class, by cobordisms, very much like we did before. And now hopefully these pictures mean a little bit more to you. They just mean attaching a 2 handle. And you can build, again, a lot of 4 manifolds by this process, simply connected 4 manifolds by attaching 2 handles, using the so-called Norman trick, which isolates each particular handle and makes it disjoint or unlinked from the rest of the stuff. And you start with some kind of again, plumbing graph, say, associated to this Kirby diagram. It could be much bigger. And then you continue attaching additional handles, in this case, making this plumbing graph into a tree. You can even start doing loops again, modulus certain provisos, and so on and so forth. So the point is, if you know what to associate to boundaries and how to do this gluing, and this is a question about this 3-3 correspondence, and that's being studied very well by now, we do. And also, if you know what to associate to each individual cobordism, you can build lots of 4 manifolds. So this is a very constructive approach, and I already try to explain to you that Nakajima's result can be easily extended to cobordisms as well. Basically, each individual cobordism gives you, at the level of partition function, some branching function of a coset model. So here is big summary of all kinds of facts about form manifolds and what they correspond in two-dimensional theories. Some of this I already explained to you. For instance, cobordism corresponds to a domain wall between theories labeled by three manifold boundaries. Gluing corresponds to fusion of such domain walls. This partition function, Vafa-Witten partition function, corresponds to elliptic genus. Its value on a cobordism is a branching function, and so on and so forth. Well, we talked about the chiral ring and Donaldson polynomials. Now, in the remaining 5-10 minutes, I want to do the following. I want to kind of switch gears and consider yet another application, ask about various moves called Kirby moves that don't change boundary, but potentially may change form manifold, and also that don't change two-dimensional theories. So these are items here and here, okay? And they'll lead to something new. So, as I explained before, some class of form manifolds can be labeled by graphs, kind of like this. Could be very complicated graph, possibly with loops, which are decorated by integers. These are earlier numbers. And let me play the following game. This can be viewed as a completely different, separate chapter from anything we did before. So in 2 slides, we're just going to discover something cool. I'm going to play the following game. Let's just even do a Abelian case. So I'll use group U1. And to every such vertex in a graph, we'll associate gauge group U1 with its gauge connection A. And unlike what we usually do, we'll try to build Chern-Simons theory, whose coefficient is this early number A. So in this case, everything is abelian, and the dots actually stand for possible fermion completion, which won't be important for me. Now, if you have a link connecting such bullets or vertices labeled by AI and AJ to every edge, we'll associate bilinear Chern-Simons term, taking gauge field of one of them and gauge field of the other, and forming this AI wedge D-AJ combination. So question is, which appeared completely for independent reasons in, say, condensed matter literature or physics literature, how do we classify all such Chern-Simons theories? So, and various people have studied it, but I'm going to ask a question: what are the operations, or what are the moves you can do on this class of theories, this quiver Chern-Simons type theories, even in the abelian case, which are equivalences? Okay, and again, we'll find something rather interesting. So suppose you have a piece of the graph which looks like this. You have one vertex with coefficient, Chern-Simons coefficient A plus minus 1. It's this guy, and the corresponding gauge field is B. I call it capital B, which is linked to only one, which is linked to vertex which has only linking number with the first guy of coefficient plus minus 1. And that will get, in our dictionary, Chern-Simons term ADA, begin with coefficient plus minus 1. The fact that they are linked together means that there is a Chern-Simons term bilinear in both. And if you try to classify such Chern-Simons actions, and if this is the configuration you have, then you may notice that A appears only in these two terms. Again, if it's not linked, if this node is not linked to anything else, then the part of the big Lagrangian or action which contains A, connection A, appears only here. So, of course, what we should do, we should try to integrate it out. And if we do this, we solve for A. It basically, equations of motion for A say that it's minus or plus B. And if you substitute everything back, so A is minus or plus B, then you substitute it to these terms, you see that you get a bunch of terms of the form BDB. Coefficients sum up in a nice way. That's why I chose these combinations with little shifts. So basically what you get is you can effectively remove this vertex, which had Chern-Simons coefficient plus minus 1. Now, what I did a very boring game. I tried to classify Chern-Simons, quiver Chern-Simons theories for you. But of course, if you now come to form manifold people and ask, after we translate this in this graphical language, what does it mean that this graph is equivalent to this graph? Well, this is an example of what's called a three-dimensional 3D Kirby move. So 3D Kirby moves are these operations on Kirby diagrams which potentially change 4-manifold, but don't change its boundary, the boundary 3-manifold. And in this case, this is operation of a blow-up, which takes a part of the plumbing graph, attaches an additional vertex with only one edge, and coefficient ±1. And the rule is that if you do that, this coefficient also has to change by ±1. So then you can continue playing this game. This is almost complete set of three-dimensional Kirby moves. Again, you see that you have these operations of blow up and blow down, where you can create a vertex or destroy a vertex with coefficient ±1, and then it shifts the other guys. If you have some vertex with Euler number or Chern-Simons coefficient 0, you can just destroy it, and then everything else becomes detached. And here is another move. So all these Kirby moves are hard to remember, but I want to give you a general principle. If you look at this dictionary and try to think of these Kirby diagrams or plumbing graphs as quiver diagrams for Chern-Simons theories, it's actually very easy to remember what the Kirby moves are. These are some operations which typically involve vertices of numbered by ±1 and 0, and morally they're just equivalences of these Chern-Simons theories corresponding to this Gaussian integration or even something simpler. For example, here I give you an example of this type of Kirby move where you have something labeled by 0. It's even easier. See, if it's labeled by 0, it means that this gauge field doesn't even get Chern-Simons term. Its own Chern-Simons coefficient is 0. So it's only linked to the other vertex, which I labeled by field B. It corresponds to field B with coefficient, Chern-Simons coefficient A. And A appears only in this bilinear coupling, which has to do with the edge. So therefore, if you try to integrate it out, this A appears as a Lagrange multiplier, and integrating it out basically forces B to be pure gauge because of this term, and that's why everything that involves B disappears. So that's a very simple, again, field theory proof, if you wish, or explanation of 3D Kirby calculus.
Does exactly the same argument work in the non-abelian case?
A non-abelian case is a little bit more interesting. So unfortunately not. Unfortunately it's, well, no, the conceptual part does work in the same way. You basically ask, I classify quiver Chern-Simons theories, and again you recover these 3D Kirby moves. So when I presented this to Mike Friedman during this year, he said that it's actually a very nice way to remember Kirby moves because everybody constantly gets confused. If you work with them, you know that it's hard to remember which way you're shifting these early numbers up or down. So this gives you machinery, how to remember it, basically. It's classifying Chern-Simons, the quiver Chern-Simons theories. And again, that's one application of this correspondence. In the remaining 2 minutes, I want to mention application in a completely different direction, which came as a surprise. So in this part of the dictionary, which involves 4 manifolds, we asked, what about 4D Kirby moves, which correspond to so-called handle slides? These are moves which are supposed not only to preserve the boundary, but also preserve the 4 manifold. So this should be some kind of equivalences of 2-dimensional theories. And this came as a big surprise because corresponding symmetries or equivalences of 2D theories were not known at that time. And therefore, this is where mathematics gave some prediction about physics using this 2D, 4D dictionary. In particular, even in the abelian case, it gives rise to identity. This is certain contour integral for which represents this equivariant elliptic genus I mentioned earlier, that basically packages instanton Euler characteristics, Euler characteristics of instanton moduli spaces. And if you translate it to physics, again, now going backwards, so in the previous example, I went from 3-dimensional physical theories recovering Kirby moves. Here I'm going backwards. I start with Kirby moves and try to interpret what it means for physics. For physicists, it means that this integration has to do with U1 gauge symmetry, and it contains some theta functions in numerator, denominator, which correspond to various types of chiral multiplets on 2 dimensions. Boils down to just the product of theta functions, so there is no integration on this side. It means that this 2-dimensional theory has no gauge group and has only matter multiplets, which contribute to elliptic genus as a factor of a theta function. So what it does, it says that there is an equivalence between 2-dimensional super QED, abelian theory with a bunch of charged multiplets and some free multiplets. And even this statement was actually not known back at the time. So that's a non-trivial duality between two-dimensional theories. So I have to put certain decorations on it. In particular, there is some kind of twisted superpotential which makes it non-anomalous. But this phenomenon is already quite interesting at a physical level, because if you look at it carefully, what happens is that these free multiplets, chiral multiplets on this side, are basically mesons which are made of field phi, which carries charge -1, and field psi I, which carry charge +1. And general principle, same as confinement, which is what happens even in abelian theory in 2 dimensions, says that you can only have combinations of total charge 0. And in 2 dimensions, this is especially a strong condition, which happens also even in abelian theory. What's cool is that then you can push it to non-abelian theory. This is kind of analog of question that Ezra asked me a moment ago. And here you get something completely insane by physics standards, because until this point, there was no single fact in the literature about non-abelian 2-dimensional theories with this amount of supersymmetry. So again, mathematicians may not be excited about it, but in this whole story, as a physicist, I'm most excited about this fact, because these theories are of very special interest to physicists. They play a very important role in string theory, and nevertheless, until last year, there was no single statement about non-abelian theories of this kind. And this is a completely new non-trivial duality, which, again, to me is the most interesting prediction that comes from these Handel slides, from 4 manifolds. If I wasn't studying 4 manifolds, I would not come up with this duality. Now, everyone talks about fantasies. Yuri Ivanovich spoke about fantasy of Penrose, and then we all mentioned words gravity and speculation, so I'll finish with one speculation, which hopefully will help to remember what we talked about. I talked about graphs. So 4 manifolds in this context are labeled by these plumbing graphs, and plumbing graphs also come up in study of A model. In particular, these are very nice papers that influenced me when I was younger. So work of Maxim with Yuri Ivanovich in particular, and Nikita's work on which mentions trees in a very, very explicit way. So of course, when you have a toric target space X, then studying rational curves and maps into that space boils down to combinatorial problem, which is essentially sum over trees and graphs. And if you think, again, in a very speculative way of these trees and graphs being plumbing graphs of 4 manifolds, such problems basically boil down to summing over 4-dimensional topologies, or 4 manifolds labeled by plumbing graphs. So therefore, one may think whether 4-dimensional gravity, which has this bubbling, fluctuating structure and sums over different geometries, is some sort of A model. So that's a wild speculation, and on this I would like to wish Maxim many more years of inspiration to people like me.
Thank you for this nice visual talk. Any questions?
Yes, so for Handel slides, there's something like a pentagonal relation. If you look several of them, which is kind of similar to the probably relation to the logarithm and other appearances. Do you get something like this? If you like compose one Handel slide over the other, over the third, there is some kind of...
No, I don't. I know that there are some... Unfortunately, we had this in 3D correspondence. There was indeed a very nice dictionary between Pachner moves of triangulations of 3 manifolds and the corresponding operations in field theory. But even in that case, the story breaks down, because unfortunately those triangulations don't capture all flat connections. And again, in the end, it doesn't quite work. So even that story is poor. In 4 dimensions, it gets worse, because not all 4 manifolds are triangulable, and PL structures are very different. So that's already a bad sign. So I only thought about triangulations of 4 manifolds in this case. I don't know this operation that you're referring to, where you have something like pentagonal Handel slide. I mean, I would like to hear more about it. Yeah.
Yeah, it's next to the last slide, yeah, it's easier. Yeah, but here, yeah, but numeration of torus section. Yeah, I remember this was it's some kind of Feynman diagram calculus, which was never interpreted as some field theory because you get some integer weights, and now it says it's 4D manifold topology.
Yeah, so here I'm suggesting that maybe this Feynman type calculus also gets connected to plumbing graph. Yeah.
As interpretation, yeah. Torus section.
Yeah, certainly composition of this Feynman graphs makes sense because this is basically gluing over 4 manifold. So, and yeah, I think it's a natural question again for at this level, just a speculation, of course.
So you had these Kirby moves for these Chern-Simons theories. Is it possible that they could be changes of Lagrangian in BV formalism, or is that too much to hope? Or is it? Have you thought of it? Because what you did in the abelian case looked a lot like a change of Lagrangian in some ambient BV.
Yeah, and maybe it is. I want to emphasize that this is, for instance, not the same. Like a politician, I'm going to answer a slightly different question. So when I first thought about it, and again, people like Mike Friedman and others say, oh, wow, this is great way to encode these Kirby moves, which we never can remember. But then I was thinking whether this is really a property of quadratic forms or Lagrangians or physical theories. And I think it is actually indeed the right question to ask, because after all, these are all closely connected. And I was doing baby operations, which you can definitely write in terms of quadratic forms. But unfortunately, it's not quite, because what happens here is that even the basic fact that you can add, in these relations, you can just add a vertex, which is completely isolated, labeled by, say, +1 or -1. That's a trivial Chern-Simons theory, because it's Hilbert space of U1 Chern-Simons theory at level 1 is one-dimensional, so it doesn't affect anything. But of course, at the level of quadratic forms, it wouldn't be equivalence. I mean, we're changing the rank and in a non-trivial way. So again, I'm giving you a slightly different answer to slightly different questions, saying why mathematicians may not have thought about it, because it's not just equivalence of quadratic forms, which would be cool. But no, it's equivalence of Chern-Simons theories, even abelian ones.
On one side of your picture, you were considering gluings of four-dimensional manifolds bounded by three-dimensional manifolds. On the other side, you're looking at two-dimensional theories also supposedly glued through three-dimensional theories. I'm doing this computation 6 minus n equals n.
Right. Yeah, that's correct. That's the.
Do you know how to compose, say, two-dimensional theories through three-dimensional theories?
Yeah. So these two-dimensional theories are kind of like interfaces, and or physicists call them domain walls. And the composition, the process of composition, is basically composition of domain walls. So literally, you can imagine three-dimensional space with a bunch of planes sitting next to each other, and then you ask, once you collide them together, or put this like a sandwich, right? What is it? So, and there is a very well defined process how to study this. So for physicists, this is already a good enough answer.
The walls are three-dimensional between two-dimensional objects.
Well, the dictionary is that the dictionary is perverse. So if you have three manifold, you get a three-dimensional theory. If you have a four manifold, which say could be cobordism, then you get a wall between two phases of three-dimensional theory. So they all together they always have to sum up to 6. That's the idea. That's if you forget everything else from this talk, that's the only thing you have to remember.
Okay, I think we are behind the schedule, so let's make a break for 15 minutes.